today we're going to start talking about polynomial functions. But before we do that, we just have to review factoring polynomials as well as solving polynomials. This is all kind of stuff we've done before. It's just a matter of now we have to take it a step further. So if I look at these first examples, it says factor the polynomial completely by writing it as a product of linear factors. So I'm going to highlight where it says linear factors. When something is a linear factor, what does that mean? Well, that means it has a degree of 1. So I want to be able to factor all of these polynomials to where each factor has a degree of 1. Each factor is just doesn't have any exponents, so it would be like x plus 2 and x plus 3. Those are all examples of linear factors. So I'm going to go over and start looking at number 1. So I want to factor number 1. So when it has x to the 4th, it's still the same double parentheses to factor, but instead of x and x to make x squared, how do I make x to the 4th? Well, that's x squared and x squared. So now I just do it the exact same way as before. I need factors of 3 that make negative 4. So factors of 3 that make negative 4 are negative 3 and negative 1. So notice if you look at both of these factors, x squared minus 3 is not a linear factor because it has x squared, and x squared minus 1 is not a linear factor because it also has a degree of 2. So I have to factor further. So which one of these can I factor more? Well, I can factor the second one, x squared minus 1, further because it's a difference of squares. So I can say x plus 1 and x minus 1. So that's factoring that one. But if I take a look at this example, I can't factor it. So I'm going to instead go up here and I'm going to solve x squared minus 3 equals 0. And I'm going to figure out what x is so then I can factor it as in linear factors. So I would say x squared equals 3, and then x equals plus or minus rad 3. So now when I come and write it in my answer, it's going to be x plus rad 3 and x minus rad 3. So these now are all factors of my polynomial, and they're just in linear factors. So let's go ahead and let's look at number 2. So number 2, I first have to take out a GCF. So a GCF has a 3x in it. So if I take out a 3x, I'm left with x to the 4th minus 16. So, okay, I'm now going to factor this. This is going to be x squared and x squared. So now I have minus 4 and I have plus 4. And I can't forget that 3x. So now if I factor this one further, it's going to be x plus 2 and x minus 2. I can't factor x squared plus 4 because it's not a difference of squares because it has a plus sign. So I'm going to take this and I'm going to bring it up here and I'm going to solve. X squared plus 4 equals 0. So x squared equals negative 4. So square root, square root. So x is going to equal plus or minus 2i. So now I'm going to come in and write x plus 2i and x minus 2i. So notice each of my factors have a degree of 1, which means I'm done. So I want you to attempt number 3 on your own, and then you can go ahead and unpause this video and I'll explain it, just so I want to make sure that you're getting the right practice that you need. So if I go ahead and solve this, I got to factor by grouping. So I'm going to take out an x squared, so I'm left with x minus 2. And over here I have to take out, a 9. So I'm left with x minus 2. So I'm left with x squared plus 9 and x minus 2. So x minus 2 is a linear factor, so now I have to factor that one. Because it's a plus sign, I have to solve it. So I have x squared equals negative 9. So x equals plus or minus 3i. So I have x plus 3i, x minus 3i, and then I also have x minus 2. I know I'm done because all my degrees are 1. So let's now go ahead and start talking about solving. Solving is the exact same way as before. You factor, and then you split it up, set it equal to 0, and solve. So if I look at this first one, I'm going to take out a y squared, so I'm left with y minus 5 equals 0. There's nothing left I can do, so I'm going to go ahead and split these up, and I'm going to solve. So I have y squared equals 0, so y equals 0. That's one answer. And over here, y equals 5. I'm done. Come over to this number 2, let's check it out. So if I look at number 2, I have to make it equal 0, just like before. So x cubed plus 3x squared minus x minus 3 equals 0. I have 4 terms, so I'm going to have to factor by grouping. I'm going to take out an x squared. I'm left with x plus 3. Over here, I have to take out a negative 1. I'm left with x plus 3. So I have x squared minus 1 and x plus 3 equals 0. Now, because you're solving, you technically don't have to put these into linear factors if you don't want to, because you can go ahead and solve it, because we know how to solve squared. When we have x squared, we would just square root it. But if you wanted to continue to factor it, you could say x plus 1 and x minus 1, and then you could say x plus 3 equals 0. So now I can say all my answers. X equals plus or minus 1 and negative 3. And I'm done. Let's go ahead and let's try number 5. I lied. Let's go ahead and do number 3, and then we'll skip to number 5. So I'm going to erase this, and just so I have enough space. All right, so if I look at number 3, I have an x to the 4th, which means it's going to be x squared and x squared. Factors of negative 36 that make negative 5. Negative 9 and positive 4. So x over here is going to equal plus or minus 3. Again, I could factor it if I wanted to, but I just added 9 in my head to the other side, and then I just square rooted it. On this one, x squared is going to equal, subtract 4, so I'm going to get an imaginary number, so plus or minus 2i, and I'm done. Again, I could have factored those further to linear factors if I wanted to, but I didn't have to. All right, so let's go ahead and do number 5. So number 5, I'm going to subtract 6x cubed. So I have 3x to the 4th minus 6x cubed plus 12x squared. So now I'm going to take out a 3x squared. So now I'm left with x squared minus 2x plus 4. So if I look at this, x is just going to equal 0. So that's one answer. What about over here? Can't solve that yet. I got to factor more. Are there factors of positive 4 that make negative 2? No. So what do I have to do? Yay! The quadratic formula! So the opposite of b, plus or minus the square root of negative 2 squared minus 4 times 1 times 4 all over 2, because 2 times 1 is 2. So let's keep cleaning this up. I have 4 minus 16 on the inside. 4 minus 16 is negative 12 over 2. So now I have to simplify that. 4 and 3. So that's 2i rad 3 over 2. So if I simplify further, I get 1 plus or minus I rad 3, because all these 2's cancel out. So I have one solution over here, x equals 0, and my other solution would be x equals 1 plus or minus I times the square root of 3. So I need you to go ahead and finish all of these problems for me, please. And then you can check your answers on the answer key that's attached to Google Classroom, or we can go over it next class. So now I want to start talking about polynomial functions, and I'm erasing this so I have enough space. So here it says polynomial functions. So a polynomial function, it says the degree of a polynomial affects the shape of its graph, and so that's the first part. The degree of a polynomial affects the shape of a graph. If I have a degree of 2, or if I have a degree of 4, it's going to affect what the shape of the graph looks like. So a degree of 1 means I have an exponent of 1, which means it's a linear function, which means it graphs a line. If I have a degree of 2, it's not going to graph a line, it's going to graph a parabola because the biggest exponent is 2. So that's the first thing that it determines. And it also determines the maximum number of turning points. So turning points are the changes from increasing to decreasing. So AKA the max and the mins. So when I have a parabola that I'm just going to sketch up here, notice my turning point is my minimum because it's changing from decreasing to increasing. That's what a turning point is. So your degree can determine the maximum number of turning points. Notice in a parabola I have 1 turning point, but you can, the maximum number of turning points, so to find maximum number of turning points, if I can spell, it's the degree minus 1. So the number of turning points a polynomial is going to have is whatever its degree is minus 1. So if I have a degree of 6, that polynomial is going to turn 5 times, because 6 minus 1 is 5. So it would look like this: 1, 2, 3, 4, 5. It can look something like that. So it would turn a total of 5 times. That's what a degree of 6 polynomial would look like. So with polynomial functions, and we can determine the turning points, and maximum number of turning points. We can also determine their end behavior because their end behavior has a common pattern. So let's go ahead and look at this. A first degree polynomial is called a linear function. And a linear function always looks like this. It's a line. And this is when my leading coefficient is positive. When my leading coefficient is positive, it's going this way. So what would happen if my leading coefficient was negative? So if I came down here and did negative, what would my leading coefficient look like then? Well, a negative leading coefficient flips it over the y-axis. So that part goes down and that part goes up. So now let's talk about its end behavior. Its end behavior is x is going to negative infinity. So as x is going to negative infinity, what's happening to your y values? Well, it's also going to negative infinity. And what about when x is going to positive infinity? Well, it's going to positive infinity. So what about when you have a negative leading coefficient on a linear function? Well, it's the opposite. When x is going to negative infinity, it's going to positive infinity. And when x is going to positive infinity, it's going to negative infinity. Second degree polynomial is called a quadratic. If I can write in a pen and not a highlighter, is a quadratic. And it looks, hopefully you all know, like this. What if my leading coefficient is negative? Well, I have to flip it over I said the y-axis originally, but it's not. It's flipping over the x-axis. Flip it down like so. So now let's talk about the end behavior. As x is going to positive infinity, as negative infinity, let's do that first if I can speak tonight. As x is going to negative infinity, what's happening to your y values? Well, it's also going to positive infinity. And what about when x is going to positive infinity? Well, your y values are going to the same spot, so both are positive infinity, positive infinity. How about down here on the bottom when my leading coefficient's negative? When x goes to negative infinity, y is going to negative infinity. And when x is going to positive infinity, it's also going to negative infinity. So negative infinity, negative infinity. So let's now talk about a quadratic, nope, not a quadratic, a polynomial with a degree of 3. This is called a cubic function. So now we have to think about this actually for a second. So notice a parabola had one turning point. So I'm going to write here one turning point. What about a cubic function? It's going to have a maximum of 2 turning points. Now sometimes it doesn't have 2 turning points because it depends on the shape of the cubic function, but the most number of turning points it could ever have is 2. So a cubic function can look something like this, which you all have seen something quite similar. It just hasn't had those visible turning points in it yet, which is why I drew this like this way. So when x is going to negative infinity in this one, what's happening to your y values? Well, it's going to negative infinity. What about when it has when it's going from positive infinity? Well, positive infinity, it's going to positive infinity. So what happens when you have a cubic function that has a negative leading coefficient? Well, it's going to go this way. And notice what happens to your end behavior? It switches. So when it's at negative infinity, it goes to positive infinity. And when it's when it's positive infinity, it goes to negative infinity. Let's go ahead and talk about fourth degree. Fourth degree is going to have how many turning points? At most 3. Some don't have 3, but at most it's going to have is 3. So if I draw this, it goes down 1, 2, 3. There are my 3 turning points. So notice my end behavior, my y values, arrows are always ending in positive infinity. Now what about when I have a negative leading coefficient? Well, it's just the opposite. 1, 2, 3. And again, not every quartic function looks like this. However, it can, and this would still be considered a fourth degree polynomial. So my end behavior is negative infinity and negative infinity. So I want to notice a similarity between positive leading coefficients, their degrees, and their end behavior. So notice on a first degree, it was negative, negative, positive, positive. And on a third degree, it was negative, negative, positive, positive. But on a second degree and a fourth degree, they were all positive. What's a good rule to remember that? Well, we can talk about, we can sit here and we can talk about how even and odds have relationships. So I'm going to write over here, an even, if it is a positive leading coefficient, if it's even, my end behavior is infinity, infinity. If it's odd, if my degree is odd, it's negative, negative, positive, positive, which means negative infinity goes with negative infinity and positive infinity goes with positive infinity. And you can write this any way you want. If I have a negative leading coefficient, notice it's the opposite. So for an even degree, so a degree of 2, 4, 6, 8, 12, 14, 22, it's negative infinity, negative infinity. And if with an odd degree, so 1, 3, 5, 7, 11, 21, anything that's odd, it's negative, positive, positive, negative. It's just the opposite. So these are nice little tricks to help us remember where we're going. So let's go ahead and look at the next page. So if I look at this next page, it says, what will the end behavior be for a fifth degree polynomial with a positive leading coefficient. And at how many turning points will it have? So, okay, so I can do turning points really quick. It's going to have 4 because degree minus 1, 5 minus 1 is 4. So it's in behavior, so it's odd and it's positive. So it's just the same. So when x goes to negative infinity, f of x goes to negative infinity. And when y goes to, when x goes to positive infinity, y goes to positive infinity. It stays the same. So now I'm going to just sketch my graph. So when it's starting in negative infinity and negative infinity, that's over here somewhere. So start here, 1, 2, 3, 4, and ends in positive infinity, positive infinity. So something along that lines would look like your graph. So let's now talk about evaluating polynomials. So evaluating polynomials, we've done this before. I would plug 2 in for x and solve. So I'd say 3 times 2 squared plus 5 times 2 minus 2. So 2 squared is 4, and then I'd find my y value. 3 times 4 is 12, 5 times 2 is 10, 12 plus 10 is 22, minus 2 is 20. So f of 2 equals 20. If I come over here, go ahead and try this next one on your own. You should hopefully get to 27. Fortunately, in a second, I'm going to find out if I'm right or if I'm wrong. So this method works, no problem with it. It's not hard, right? It's just kind of a nuisance because we don't really like PEMDAS because PEMDAS is easy to screw up. So synthetic substitution also works to evaluate a polynomial function. So if I want to evaluate a specific x value and find the y value, I can use what's called synthetic substitution. So synthetic substitution is set up the exact same way as synthetic division. This number goes on the outside in your box, and then I write the degrees of, or the coefficients of all my degrees. So 3, 5, negative 2. Make sure you didn't skip any degrees along the way. So now I'm going to draw my bar. 3 gets dropped down. I multiply 3 times 2. 3 times 2 is 6. I now add. 5 and 6 make 11. I'm now going to multiply 11 and 2. That would be 22. I'm now going to add. I get 20. This number, when we were doing synthetic division, was your remainder. But when I'm doing synthetic substitution, that's your answer. So I have f of 2 equals 20. And notice this answer is the exact same answer I got up here because it's the exact same problem. If I come over here and I do number 2, put negative 2 in my box. I'm now going to write down all of my coefficients, but make sure you have all your degrees. So 3, 2, 1, none. So perfect. So negative 2, negative 7, 1, negative 1. Bring down negative 2, multiply negative 2 and negative 2, you get 4. Add them up, you get negative 3. So now I'm going to multiply negative 3 and negative 2. I get 6. That makes 7. I'm now going to multiply 7 and negative 2. That's negative 14. So I get negative 15. So f of negative 2 equals negative 15, which means I either did something wrong down here or I did something wrong up here. So I told you I was going to make a mistake, but I was just warning myself and warning you. So let's see if I can figure out what I did wrong. I got it. Alright, so I'm glad I was keeping you all on your toes. You were probably sitting here thinking, she was doing it wrong, and you can't yell at me because you don't see me. I forgot to put that squared up here, so I did go ahead and redo it down here, and I did get negative 15. So this way is the totally wrong way, but I was just testing your limits and you didn't know what you were getting into watching this video, but I hope that didn't frustrate you. So the nice thing about synthetic division is I personally think it's a little bit easier. PEMDAS is kind of easy to mess up, as we can tell by my valid mistake up here. So synthetic substitution works lovely to get your answer because that remainder number would be your answer. So you're going to do number 4 and number 2. Clearly I can't count on this worksheet or follow PEMDAS. So you're going to do these 2 problems that I circled. You're going to finish all of the problems on the front. And then we will continue with this note sheet next class.